Hello, for our first question, we are going to find the saddle point for the matrix game having a payoff matrix as our 3 by 4 matrices we have here. I'm gonna have the definition of a saddle point being if the mat payoff matrix of a matrix game contains an entry Aij that is both the minimum of row I and the maximum of column J. So first, we go through all our rows. We find the minimum of each of the rows. We get 3, -5, and 3. So for those, I'm going to circle them. We'll get back to that later. Next, for all the columns, I'm going to find the max of each column, which we get 5, 3, 7, and 3. So we're going to box all of those numbers. Now, when you combine both the minimum of each row and the maximum of each column, that's where you get our saddle points. So if you overlap those two matrices that you see in the middle of the paper, you see that the threes in row 1 and the threes in row 3 are the saddle points. It is also clear that 3 is the maximum of the row minima and the minimum of the column maxima. So we get 4 saddle points here, which is A of 1, 2, A of 1, 4, and then A of 3, 2, and A of 3, 4. And those are our saddle points for our matrix game. Next question number 2, we're gonna let M be the matrix game having the payoff matrix of this 3 by 3, and we're gonna find the expected payoff V of X and V of Y for two separate X and Y values. So for part A, we have X is 1/3, 1/2, and 1/6. Y is 1/4, 1/2, and 1/4. So the formula for our expected payoff E of X and Y is X transpose A times Y. A is just the M matrix that we have at the beginning of the question. So we're going to take our X, transpose it, multiply it by A, and then multiply it by Y to get 13/12. Next, we're going to find V of X, which is defined as the minimum of E of X and EJ for 1 is less than or equal to J, which is less than or equal to 3. So we're basically going to take our X values and multiply them by each of the columns of A and then look for the minimum value. So when you do that, you get 5/6, 1, and 9/6. So the minimum of that would be 5/6. V of Y is going to be the opposite. It's going to be the max of E of EJ and Y for 1 is less than or equal to J, which is less than or equal to 3. So we're going to do basically the same thing here, but we're working with the rows now instead of the columns. So we can multiply our Y by each of the columns and look for the maximum. So we get 3/4, 3/2, and 1/2. The maximum of that is 3/2. And it's important to note that V of X should be less than or equal to the expected value or the expected payoff E of XY, which is less than or equal to V of Y. And that is true with 5/6 being less than or equal to 13/12, which is also less than or equal to 3/2. For part B, we're basically doing the exact same stuff, but just with a different X and Y value that we were given. So for our expected payoff, E of XY, that's equal to X transpose AY. We're gonna do the exact same thing, multiply those three matrices out, you get 9/8. V of X is once again the minimum. So we're gonna take our X values and multiply it by each of the columns and look for the minimum. We have 1, 3/4, 7/4, so the minimum is 3/4. V of Y is gonna be the maximum. And we're going to multiply our Y values times each of the rows. We get 1/2, 5/4, and 3/2. So we get the maximum there being 3/2. And once again, V of X is less than or equal to E of X and Y, which is less than or equal to V of Y, with 3/4 being less than or equal to 9/8 being less than or equal to 3/2. Lastly, we're going to minimize the function 2x1 plus 3x2 plus 3x3, subject to the constraints x1 minus 2x2 is greater than or equal to -8. 2x2 plus x3 is greater than or equal to 15. 2x1 minus x2 plus x3 is less than or equal to 25. And x1, x2, and x3 are all greater than or equal to 0. First step here, we're going to change it to a maximized problem. So we're going to take our function, multiply by -1. So basically just switch around the positive or negative signs. And then you're also going to do that for the constraints to making them all uh, the function less than or equal to a constant. We're also going to keep our x1, x2, and x3 all greater or equal to 0. This is called the canonical form. So we're going to set m equal to the new function with all negative signs. And in order to make that equal to 0 on the right-hand side of our table, we're just going to bring over all the values where we have our original function plus m is equal to 0. I wrote down that function along with all the constraints, as it makes sense when you put it into table form where all the coefficients go. So that's what I did for our first table. And now we gotta start looking for pivot points. So we have a negative 15 on the right-hand side. We can't have that. So we know we're going to use that row to find our pivot. And we're going to try to find the smallest ratio of values in that row. So the smallest ratio would be 15 over 2 versus 15 over 1 as it's smaller. So we're going to make that row and that specific pivot point 1, and we're going to cancel out everything in that column to make the rest of it zeros using row operation techniques from linear algebra 1. After that, we have a negative 7 on the right-hand side, so we're going to do the exact same thing. We're going to find the smallest ratio in that row and then make that our pivot point. We have two negative 1s in that row. So you look at the last row, you try to find the biggest coefficient, which in this case is the 2 over the 3.5. So we have row 1, entry 1 being our pivot point. Once again, to make that 1 and the rest of the column 0, we're going to divide by negative 1 and then just clear out the rest of that column to zero it out and then do that for the entire row. In our third table, we got rid of all the negatives on the right-hand side, and it would make sense to just do x3 and be done with the question, but if you did that, it would make everything else negative and kind of mess up your progress. So I found the largest coefficient in the last row, I mean, which is 7/2, and then I looked up in the first three rows to figure out uh, the ratios. So I got x5 and row 3 to be the new pivot point. So I'm gonna make the 3/2 1 and then clear out the rest of x5 using row operation techniques, which is seen in the next table. And then now we have an x3 uh, column without a negative sign, so it won't mess up the previous progress. So now we can go back to x3 and clear that out to make it a 1. So you would divide that by or multiply by 3/2 and then clear out the rest of the column, make it all zeros. And then once again do the row operation techniques to the rest of the rows in order to make that happen. Lastly, we just have our x1 column to worry about. So we're gonna make that 1, clear out the rest of the columns using the row operation techniques. This is all using the simplex method. And when we do that, we have our final table, which has x1 being 19, x2 being 13.5, and x3 being 0. And then we have our m value, which is 78.5, as you see in the bottom right-hand corner. So when you plug it into our function, which is 2x1 plus 3x2 plus 3x3, the table kind of does it for you already, and it gives you the final answer of 78.5. I didn't stop there. I went to a graphing calculator and tried to solve it just to check my answer, like double check, make sure I was right. And if you look back to the previous table, we had a 58 over 3 and a 41.3 or 41 over 3 in one of the previous tables, and that those numbers are very close to our x1 and x2 values. But the final answer gave you a m value greater than what we got. So that's how we know that our answer is minimized and is the optimal solution for this problem. I hope you guys learned a lot in this problem and in these questions, and I'll see you guys later. Bye.